Hi everyone, welcome back to the channel. In today's video, we will discuss what is known as PPV theory for oscillators. So let's get started. So PPV stands for perturbative projection vector. And this is known as a PPV model for oscillators. It's very useful for phase noise and for injection locking as well. And in the last video before this, we discussed some of the mathematical preliminaries that you need for the PPV model. So let's get into it. This will be sort of a long video. I mean, I can divide it into several videos, but I decided to do one long video because that keeps the flow going. But if you can make it all the way till the end, then I really would think that's great, right? So, okay. So in previous videos, we discussed the ISF model. So let's maybe recap in sort of in essence what it meant or what it was saying. So the ISF model said that, let's say this is part of my limit cycle, right? And I introduce some kind of perturbation to this limit cycle. So let's say the perturbation is like this in some direction. Then, although we didn't state it explicitly, ISF model kind of says that this can be decomposed into an orthogonal basis where I have one component that is tangential to the limit cycle and one component that is normal to the limit cycle. And we said that the normal component only contributes to an amplitude deviation that dies out with time, whereas the tangential component has only a phase contribution, which remains constant with time. It is only a phase deviation, right? So that's kind of what the ISF model said. Okay, and I should probably specify that this is an orthogonal basis, right? So I should say that this is an orthogonal basis decomposition. And the reasoning was given that, okay, it said it's not really a rigorous kind of reasoning behind why this happens. It was just sort of a heuristic or heuristic arguments were given, right? So what we'll do today is we are going to discuss a different model, called the PPV model, which was developed by Alper Demir and J.G. Roy Chowdhury. And I'll leave a bunch of references in the description. So what they claim is that given the same kind of limit cycle, if I have some perturbation, then this perturbation can be decomposed into a tangential vector of a specific length, right? So it has to be of some length. Maybe it's a bit longer or a bit shorter. We don't know that. And if you have this vector, then of course, the other component would be like that, right? Which is the same as this. So this basis, so this is a basis, right? This vector and the blue vector, they form a basis, but they are not orthogonal now, right? So essentially, so these two add up to give you the black vector. And they again say the same thing, that in this oblique basis, the blue vector only produces phase deviations and the green vector only produces amplitude deviations. Okay. So that's sort of the essence of PPV model. It says that given any perturbation, there is a very specific vector along this tangent plane or tangent line, a specific vector of a specific length. And the length of this vector is determined by the perturbative projection vector, which is another vector. It's not this vector. The PPV, which also determines the eventual phase that is generated. So only the phase contribution, that the phase deviation that it adds is determined by the PPV, and the length of this vector is also determined by the PPV, which we'll see what that is when we derive it. So it says that if you have a specific decomposition along this oblique basis for a given perturbation, then this component produces only phase shift, and this component produces only an amplitude shift, which dies down with time. Okay, so this is an oblique basis decomposition. Okay, so that's what the PPV model is. So if you want to compare the two, then I would say, ISF model is somewhat simple. Mathematically, at least, it's fairly simple. You don't need to know too much. It's just some convolution and some simple, just convolution really, and some nonlinear dynamics, right? But it's good enough for intuition, right? For design intuition. So we saw that, they provide a relationship between the C naught term in the ISF and the flicker up conversion, right? So we see that, okay, when C naught goes to 0, flicker ISF consumption up conversion also goes to 0, which is correct, more or less correct, right? But it's not exactly rigorous, and we saw that there are two assumptions that they make. One is the linearity assumption of the phase, and the other one is this orthogonal decomposition that you can do, right? And both these assumptions are not exactly rigorous. They may be still correct in some cases, but the PPV model sort of corrects for that. So this is actually mathematically rigorous with proofs, things like that, chooses the right mathematical approach. And you can use it for faster computation. So we saw that ISF requires sort of a time domain computation, which is long, whereas PPV can be directly calculated actually using a periodic transfer function. And in my opinion, at least, it gives you a slightly deeper insight into the mechanisms of these phase deviations. And of course, this also gives you deeper insight compared to like linear models, because linear time varying model, but the PPV model is a non-linear time varying model. So it's a little bit deeper. So let's actually go ahead and derive all the results. So this is sort of the intuition behind what's going on. The mathematics is actually quite interesting, and we should look at that. So, of course, as usual, the prerequisites that you need for this are you have to have a good understanding of limit cycles. So MMIC4, the video MMIC4 in this series kind of talks about limit cycles and introduces them. And then you should have watched the precursor to this, where we talk about the state transition matrix and Floquet theorem, which is actually MMIC 15. So that's important. MMIC 14, we talk about a nonlinear analysis for a specific example of an LC oscillator, right? So just to give you an idea of what's going on, I would say these 3 videos you should watch before you start this. And then, as I said in the previous MMIC 15 video, that you have to have a strong background in linear algebra and in differential equations. Okay, so with that, we can start deriving the model. So let's quickly recap what we said in the previous video. We said that given an equation of the form x dot equal to a of t times x, which is a homogeneous differential equation, then the solution for the homogeneous case can be given by phi of t comma 0 times x naught, right? This was the homogeneous case, where the phi here is the state transition matrix. Okay. And then we said that if you have an inhomogeneous equation, a of t x plus not v plus b of t, then the inhomogeneous solution is given by the homogeneous solution plus the particular integral, right? Which is integral 0 to t phi of t comma s b of s ds. Right? So we kind of looked at these results in the previous video. And finally, we said Floquet theorem says that, just to make a new page. And we said that Floquet theorem says that if a of t plus t is equal to a of t, so where a is periodic, implies that the state transition matrix can be written as summation I equal to 1 to n exponential of mu I t minus s times ui vi transpose, right? Ui of t times vi transpose of s. Ui of t times vi transpose of s. Right? And we also said that this vi transpose of t, the vi and ui vectors basically follow bi-orthogonality condition, right? And this will actually be very useful to us today. We'll use all of these relationships. That's why I'm kind of reviewing them. So for all time, and this is called the bi-orthogonality condition. Okay, so that's kind of what we said in the previous video. Okay, so let's get started with today's video, the new material. So I'll say PPV model. Okay, all right. Okay, so I will label these as 1, this is 2, and this is 3. Okay, so now we'll derive some new results. So if I substitute 3 into 1, what do I get? Right, I get that the homogeneous solution xh of t is given by summation I equal to 1 to n exponential of mu I t ui vector t vi transpose of 0 x of 0. Right? And that's because, of course, s is 0. So when you substitute, you basically substitute s equal to 0 here, and then you put this phi back in here, and that'll give you exactly this, right? And we can do the same thing for the inhomogeneous case. So if I say I substitute 3 into 2, then I get x inhomogeneous. So let me use black. X inhomogeneous of t is equal to the homogeneous solution plus integral 0 to t summation I equal to 1 to n exponential of mu I t minus s. Here you can't substitute s equal to 0 because we're integrating over s, right? Ui t vi transpose of s b of s ds. And you can pull the summation out because they are independent. I equal to 1 to n ui of t integral 0 to t exponential of mu I t minus s times vi transpose of s b of s ds, right? So we'll use these two relations in today's developments. That's why I'm kind of writing them out explicitly. Okay. Maybe I should say preliminaries. All right. Okay, so now that we have those preliminaries ready, let's look at the oscillator dynamics. Oscillator dynamics and Fluke theory. Okay. All right, so we saw earlier that a general dynamical system should be given as x dot is equal to some f of x, right? Some function of x. So the dynamics are determined by some function of the current state. And if you haven't seen this, an example of this is in MMIC 14, the video. Okay, where x belongs to Rn and f goes from Rn to Rn. Okay. All right. So the first step that we would like to do is to say, okay, this dynamical system has a limit cycle solution in it. So we assume, okay, there is a limit cycle solution, and then we want to find the dynamics of this limit cycle and how it responds to perturbations, right? So I'll say, okay, let xs of t be the limit cycle solution, right? So which means that xs of t basically traces out as a function of time the limit cycle, right, in state space. So at any point in time, this is your xs vector of t at t1, t2 it is over there, t3 is over here, and 4, 5 over there, and so on. So it traces out this limit cycle, and it's exactly on the limit cycle, right? So that's exactly the limit cycle solution. If you don't know what limit cycle is and what the properties of a limit cycle are, you should watch MMIC 04. That's where I cover that. And to understand oscillator theory, you cannot do it without really understanding limit cycles. So you should definitely know what that is. Okay. So since xs of t is a solution of this equation, which we'll call maybe equation 4, right? You can substitute it in and it should satisfy it, right? So which means that xs dot t is equal to f of xs of t, right? Obviously. And now what I can do is, yes, that's right. Xs dot of t. So we substituted as xs into that equation. Now, if I take a derivative on both sides with respect to t, you get what? Xs double dot of t is equal to df over dx. That's vector x at x equal to xs, right? Times dx over dt. Essentially, that's just the chain rule in vector calculus. And I can write this as some a of t times xs dot of t, right? And what is the properties of this a of t, right? This a of t is df over dx at x equal to xs, right? So of course, this is not a function of x, right? It's not function of x because it's a function of xs. You have set x to be equal to xs, right? So it is only a function of time. Because xs is a function of time and a is only a function of xs, then a is only a function of time, right? And a of t plus t is equal to A of t because xs is periodic, it's t periodic, right? Okay, so we've shown, what have we shown now? We've shown that A of t is a periodic linear transformation matrix, right? Yeah, so essentially we've shown that given given x equal to A of t, or x dot equal to A of t, x has xs dot of t as a solution, right? So this equation here is a periodic linear homogeneous differential equation, right? And we've studied that in the previous video and earlier in this video as well. And we've seen that the derivative or the velocity of the limit cycle satisfies this equation, right? This is the velocity of the limit cycle. So we've shown that the velocity of the limit cycle satisfies a linear periodic homogeneous differential equation, right? And that's very nice because now we know how to deal with them, right? Okay, so because of this implies this, there exists a state transition matrix which obeys Floquet theorem, right? So what does that mean? That means that xs of t dot, which is a solution to this equation, can be written as summation I equal to 1 to n exponential of mu I t ui of t vi transpose of 0 xs dot 0. And this comes directly from what we did in the preliminaries, right? So we said, okay, if I have a linear homogeneous differential equation, then the solution can be written in terms of the Floquet multipliers and the Floquet vectors, right? And that's essentially what I've done here. Okay, very nice. So far, so good. Let me rearrange this a little bit. You can say this is 1 to n. And I'll put this as exponential mu I t vi transpose of 0 times xs dot of 0 times ui t. So why can I rearrange them? Because product of these two vectors is now a scalar, right? And since it's a scalar, I can move this out here. This is also a scalar. So this entire thing is a scalar now, right? So this whole thing is a scalar. And this is a vector. And in fact, it's not just a vector, it's a basis, right? So we saw that these UI matrices, UI vectors in the previous video form a basis of Rn. So essentially what I've shown is that the velocity vector of the limit cycle, can be expressed in terms of the basis vectors that come from the Floquet vectors, basically the Floquet vectors, Floquet theorem. And the basis expansion has coefficients that are given by the scalar. Okay. All right. So now comes the real insight. Okay. So for some value of I, let me just say for some I, it doesn't matter what that I value is. So for some I, and just for simplicity, we say I equal to 1, right? Without loss of generality. So you can say I equal to 10 if you like, it doesn't matter. But in this case, just let's say I equal to 1, we see that if I set u1 or ui for whichever I of t equal to excess dot of t, then this ui, u1, if u1 is equal to excess dot of t, this satisfies the above equation. Okay, so let's do that. So if I set, for example, this one, if I set it to okay, sorry, I have to set this to u1 of t, right? Not u1 of t, sorry, I have to set it to, so I'll say, okay, if I make this sort of this equivalence, then this term becomes u1 vector of 0, right? And from the orthogonality condition, we know that vi transpose ui or uj is delta ij. So this only shows up when I equal to 1, right? So when I equal to 1, the product between these two terms, product between this and this is equal to 1. And for all other I values, this is 0. So this summation drops out and you're only left with this term for I equal to 1, right? And since, of course, okay, let me write that out. So now xs of t becomes exponential of mu1 of t times v1 of t 0 times u1 of 0. And this whole thing is just 1, basically. This whole thing is equal to 1. So you can kind of remove it. And ui of t, we said, is also the same thing as xs dot of t, right? So on the left hand side, on the left hand side, you have xs dot of t. And on the right hand side, you have xs dot of t. So obviously, this means that mu1 should also be equal to 0, right? So we also need mu1 to be 0. So when mu1 is 0 and u1 is equal to xs dot, then the left and right hand side of this equation are equal. And essentially, we've said that we can choose u1 to be, or not we can choose, u1 is equal to xs dot, right? With the Floquet multiplier of 1, right? So the Floquet multiplier lambda 1, do it in green, 1 is equal to exponential of mu1 of t, which is equal to 1. So that deserves another box. Okay, so these two relations we'll use a lot. Right? So we've said essentially what now? We said that the velocity vector of the limit cycle is exactly one of the basis vectors that come out of the Floquet decomposition. Okay, and that now satisfies a linear homogeneous differential equation, right? All right, so that's very useful, and that's one of the big results. Okay, so that's a result. All right. So there is a lemma which I won't prove, I'll just state it, but we'll use it later. I'll give you some intuition as to behind what it is, but this is a sort of a general lemma in nonlinear dynamics that has nothing to do with this paper itself. So if I have a system that has many different Floquet multipliers, one of them is equal to 1, and the rest of them are less than 1. So for all I equal to 2, 3, and so on up to n, then xs of t, which is the limit cycle solution, or not the, then xs of t is a limit cycle solution of x equal to or x dot equal to f of x. Okay. So that's the lemma. It just says that if I have a system that has Floquet multipliers where one of them is 1 and the rest of them are less than 1, then you get this limit cycle solution. Then the limit cycle solution exists for that system. Yeah, and that should make intuitive sense. I mean, these exponents basically, Floquet multipliers or Floquet exponents basically tell you if the system is growing or it's unstable or stable, right? So if any of the Floquet multipliers are greater than 1, then the amplitudes grow and it goes to infinity. If all of them are less than 1, then it just decays and goes to 0. Whereas if one of them is equal to 1, and the others are less than 1, then you get a good limit cycle. So that's kind of a lemma, and I'm not going to prove it, of course, but it's a general statement in nonlinear dynamics. General lemma. Okay. So in our case, we have said that since we have said that xs of t is a limit cycle, right? And we also know that one of the Floquet multipliers is equal to 1, then it's reasonable to assume that modulus of lambda I is less than 1 for all I equal to 2, 3 to n. So this is not exactly mathematically totally rigorous, right? But it is reasonable to say that if I have a limit cycle solution and I know that one of the Floquet exponents is 1, then the rest of them should be less than 1 for it to be a limit cycle solution, right? It's not really a corollary. It's sort of a equivalent, not exactly equivalent, but equivalent enough for our case. Okay. All right. So now let's go into nonlinear perturbation analysis. So what have we shown so far? We've shown that given a limit cycle, its velocity vector satisfies a homogeneous differential equation that is periodic, which gives us some Floquet exponents and Floquet vectors. And then also that this same tangential vector, or the velocity vector of the limit cycle, is equal to one of the Floquet vectors, right? That's what we've shown so far. Or another way to say that is that one of the Floquet vectors is the tangential component to the limit cycle, or the velocity vector. Okay. So now we will actually start looking at perturbations, right? So we want to introduce a perturbation to the limit cycle and see how it responds, which is kind of the basis behind understanding phase and phase noise and injection locking. Okay, so let's ground ourselves a little bit with a limit cycle. Too many equations is not good, so let's draw some figures. Let me draw that again. Something like that. Okay, so let's assume that's a limit cycle. Okay, and then I have, let's say my system is x dot equal to f of x. And the solution to the system is this one, which is xs, which is the limit cycle solution, right? And then at some point in time, I'm on this limit cycle, and I have a velocity of the limit cycle, which is tangential to it, right? So this is my xs of t at some t, and this is xs dot of t at that same t, right? That's the velocity component. So now what they say is that if I introduce a perturbation to this in the form of b of x times b of t, we'll explain what these big B and little b are. Actually, write that. Plus b of x times b of t. So essentially, you're adding a perturbation to the velocity component, right? Because So essentially I say, okay, instead of the velocity going this way, I say, okay, the velocity actually goes that way, and then there's a perturbation to it that way, right? Then I get a new velocity vector like that. So this is this x dot. This is my new x dot, the red x dot t. Okay. This is the perturbation. So if I have a perturbation of this kind, so you're kind of like at any instant of time, you're changing the velocity a little bit because of adding some charge or something like that. Then what happens to the dynamics of the limit cycle? Right? That's what we're trying to study. Okay, so we know that this original one satisfies the periodic linear homogeneous differential equation, right? Okay. All right, so what is this B, capital B and little b, right? So let's go back to some circuits maybe and see what these two things are. So B of t is a function that goes from R to Rp. And what it is at some time t, p different noise sources, p different noise sources produce a p by 1 noise vector. So essentially saying, okay, at some time t, B of t says, okay, it takes the time t in and spits out p different numbers, which correspond to p different noise sources, right? And then B, capital B of x is a matrix which goes from Rn, it's not a matrix, it's a function actually, which takes a vector Rn to a matrix Rn cross P. So what is this now? It says at some location on the state space, or I should say at state, not location, at some state x, is also location on state space, the response of the state to different noise sources. Okay, to p different noise sources. P different noise sources, right? So essentially, B takes in the state of the system and then says, okay, for this state, I have P different responses, right? So if you put them together, what does it look like? B of x times B of t. B of t is a vector. That looks like a product between a matrix of size n by p and a vector of size 1 by p, right? So here I have kind of all of these columns respond to the response for different noise sources. And here are the noise source contributions, right? So essentially what happens? I mean, this comes here, this comes here, this comes here, and so on. And then you eventually add up all these values, right? So you're weighting the different responses to the state by the contributions from different noise sources. And then you sum them up and that gives you a new state, right? A new location. So that's exactly what's going on. So each of these columns basically produces some perturbation in some direction, and then they all have to be added up at the end by weighting them with the this noise vector, right? So that's the final result is that, and that's what this B of x times B of t gives you. Okay. So note that this is not exactly an impulse perturbation like in ISF. This is a general perturbation. As it can change with time, it's not an impulse. We'll look at the impulse case at the end. a general perturbation. The fact that it's not an impulse is because we actually show that the phase response is not linear. So you can't use an impulse model. You have to use a general model, general perturbation-based model. Okay, so moving on to the next concept is a lemma, also known as a small theorem. There exists B1 of x comma t. So some kind of perturbation, B of x. So perturbation is written as B of x times B of t. And if for a specific B1, for a specific perturbation that only produces a phase shift in the limit cycle solution. Okay. In other words, you could say, x dot of t is equal to f of x plus this B1 perturbation x comma t is solved by xp, some solution, which is nothing but a phase shifted version of xs t plus alpha of t. Okay, and this alpha of t is known as the phase deviation. So what we're saying is that for a given perturbation, we'll see what that is. This limit cycle, basically, the solution to the limit cycle is just phase shifted, right? So that's the lemma. It says that there exists such a perturbation. So it doesn't tell you what exactly it is. It just says something like that exists. Okay, so let's actually prove this because it's useful to know what the proof is. Okay, so to prove this, we'll start with the limit cycle solution. Actually, not the limit cycle solution. So we essentially just take this, right, and we plug it into the perturbed differential equation, right? So we said that, okay, which is this one. So we plug it into that. Okay. So let me actually write that out. So I have x1, x dot of t is equal to f of x plus b1 of x comma t, right? So that's the differential equation we have. We have some kind of perturbation b1, and we say that there is a solution that is of this form that satisfies it. So let's actually prove that. And that will also give us the value of this b1. Okay, so let's write it out. So d over dt of xs of t plus alpha of t is equal to f of xs of t plus alpha of t plus b1 of xs of t plus alpha of t comma t. Okay. So on the left-hand side, I just use chain rule again, and I get xs dot of t plus alpha of t times 1 plus alpha dot of t is equal to, on the right-hand side, I have f of xs of t plus alpha of t plus b1 of xs of t plus alpha of t comma t. Okay. Now comes another insight, which is that we want to choose b1 of x comma t, so that perturbation, to be some scalar multiple c1, which is a function of the state, the phase deviation, and time. It's essentially just a scalar times u1. of t plus alpha of t, right? And we showed earlier that this u1 vector, this is a vector, is the limit cycle velocity, right? Xs dot. So you're saying if we choose the perturbation to be along the tangent to the limit cycle, then only a phase shift is produced, right? We haven't proven that yet. We've just said that, okay, if we choose this, let's see what happens essentially. Right? So that means that it's not exactly at the tangent. It's, so we basically choose B1 vector to be tangential to the limit cycle at t plus alpha of t. So note that it's not tangential at t. It's tangential at t plus alpha of t, right? With a scaling of C1. Vector C. That's just a scalar. So we'll see what that value is. Okay, so if we do that, what do we get? So then we get on the left-hand side, it's the same thing. T plus alpha of t, 1 plus alpha dot of t is equal to, on the right-hand side, we know that f of x is the same thing as x dot, right? So we can replace that with xs dot of t plus alpha of t. For the original, since xs is the original limit cycle, it's not the shifted version, it's not the perturbed version. It's on the limit cycle, and that solution satisfies f of x equal to x dot. That's why we can replace that over there. Plus, now b1 is going to be written as c1 of x, but x now is xs of t plus alpha of t, comma alpha of t, comma t, times u1 of t plus alpha of t. So I just made some substitutions really, right? Okay. All right. So now we know a few things. We know that this thing on the left is nothing but u1 of t plus alpha of t from the previous section. Which is the same thing as this u1 vector of t plus alpha of t, right? So the only conclusion is that these two left and right hand side can be equal if alpha dot of t is equal to c1 of xs of t plus alpha of t, comma alpha of t, comma t. So if the derivative of the phase shift is equal to that constant, then we satisfy this relationship, and we have shown that only a phase shift is produced for an excitation of this kind. So essentially, another way of saying this is that if the perturbation is along the tangent with a very specific C1, or this very specific scalar value for a given alpha, for a given phase shift, you have a specific scalar value that you need to perturb the system with, then only a phase shift is produced, right? So we have essentially three different things here that are related. So, I mean, you can only do this because you can cancel this u1 term on both sides, and the fact that you can cancel it because u1 is not 0 for all of time, right? So that's like a technical detail, but it's not important. Okay, so that actually completes the proof. Okay, so let's actually do some intuition. So let's build some intuition behind what this is trying to say. Okay, so again, draw a limit cycle, something like that. And we have some current state, S of t. right? And this was going along this direction, xs dot of t. That was its velocity component, right? This nice velocity vector here. But now what happened? Now you perturbed it with some b1 of x comma t. What is this b1? Okay, let's just say, okay, you perturbed it with some b1. So now this new velocity component is something like this, right? And this new velocity component has moved your vector or your state, let's say from here to here, right? So this is a phase shift of alpha of t. This is xs of t plus alpha of t, okay? And at this location, there is a tangential vector, right? So this theorem is saying, or the lemma is saying that this tangential vector is the perturbation. If the tangential vector at this location is along the same direction as the perturbation that you introduced, only then this is satisfied. Only then a phase shift is produced. That's what it's saying. Xs of t dot, not t. This is xs of t plus alpha of t dot. And we said that this is equal to u1 of t plus alpha of t. And we showed that this must be equal to, so we said b1 should be equal to c1 times u1, right? So this vector, the perturbation, if it is along the same direction as this vector with some scaling factor c1, then this limit cycle essentially is shifted along its trajectory to this point. Of course, it cannot be shifted like this and then come back there, because then you have two solutions that meet at that point, and that's not allowed, right? So it has to be shifted only along this limit cycle. Another way of thinking of that is to say that, okay, if this alpha of t is smaller and smaller, you still need to be on the limit cycle for all values of alpha of t, right? So when alpha of t is smaller and smaller, C1 becomes smaller and smaller. As you can see kind of here, they're related. So when C1 becomes smaller and smaller, B1 becomes smaller and smaller. And then this perturbation becomes closer and closer to the original tangential vector, and you move along this curve. And so that's what it's saying. So that's the intuition behind what's going on there. Okay, so let's actually write a few sentences down now. So what are the key insights, right? So these are sort of my insights, I would say. It's not from the paper. Okay, so u1 vector, it's a vector which comes from the Fouquet decomposition, determines the phase deviation. Okay, and then we see that u1, a alpha of t, and c1 are all related. Right, and just to give you a preview, this u1 is where the perturbative projection vector comes from. That's why it's showing up literally everywhere, right? We'll see what the PPV is, but it's very closely related to this. Okay. And the third insight is that B1 of x comma t is the perturbation that pushes or pulls. So this is from the paper itself, actually. The state along the limit cycle. Okay. So So it never leaves the limit cycle. This is very important. Okay. Maybe I should say never leaves the limit cycle when B1 is applied. Okay. So that's nice. So we said that, okay, we have this sort of perturbation that we know if we apply this perturbation, then we get a specific phase shift and no change in amplitude. And that perturbation is along the tangential component given by U1 at t plus alpha of t. So they're all kind of related by these relations, right? We still don't know what is the C1 actually, right? If we know what is C1, then we know what is B1. And from that, we know what is alpha, right? Actually, from C1, we can directly get alpha. So we need to know what is this C1, right? We just said, okay, it's some constant, but we don't exactly know what it is. So that's sort of the last piece of the puzzle, right? What is C1? And hence alpha of t. That's what we would like to find out now. Okay, so to do that, we need to actually consider the general case and not the specific perturbation. So say B of x, B of t is a general perturbation. So it's not one that only moves along the phase, along the limit cycle, right? Implies it produces both phase and amplitude deviations. Okay. Then what we can say is, okay, given this random perturbation, we can remove the part of it that produces only phase, implies that B tilde of x comma t is this general perturbation minus the one that produces only phase shift. Okay, so it's kind of defining it basically. The rest of the perturbation. Okay, all right. So we know that the UI vectors are a basis for Rn. We can expand the general perturbation B of x times B of t in this basis, right? Of course, this is a vector in that space, so and UI is a basis. Actually, it's not necessarily an orthogonal basis, so that's very important to keep in mind, and that's where the oblique basis comes from. But we'll see that. So that means that I can write B of x, B of t as a summation over I. So this is just basic linear algebra, right? X comma alpha of t comma t times ui of t plus alpha of t. So I'm choosing this basis, ui of t plus alpha of t. So maybe I should, doesn't matter, since ui is a basis for all t, you can say, okay, ui of t plus alpha of t is a basis, and I'll expand it in that basis, and then these are the coefficients of the expansion, right? Very nice. Okay, then what is ci? Implies that ci is given by the biorthogonality condition. condition, right? And if you know linear algebra, then you can pretty easily see this is that is the inner product of VI transpose with B of X, B of T, right? Since VI transpose Uj is equal to delta Ij, right? So essentially you multiply VI transpose on the left side here and the left side here, and all the summation terms drop out except for when V1 is equal to U1, and that pulls out this CI component, right? That's what I'm doing there. Simple linear algebra again. So from that, we get a direct answer for what is CI. So CI is X comma alpha of T is equal to VI transpose of T plus alpha of T, B of X, B bar of T. Very important relationship. Okay. And we know that B1 of X comma T is C1 of X comma alpha of T comma T times U1 of T plus alpha of T. Right? So the first part, basically C1, U1 is taken up by B1. So whatever is left is B tilde, and that should be the summation for the rest of the components, right? Implies that B tilde of X comma T is nothing but the summation over the rest of the terms, 2 to N. Ci of X comma alpha of T comma T, Ui of T plus alpha of T. Okay. And we know that alpha dot of T is C1, which we got from earlier, which implies that the derivative of alpha of T is C1, but we know C1 is VI transpose B BT, capital B small t, right? So that is nothing but V1 transpose of T plus alpha of T times B of X times B bar of T. And this is probably the most important relationship of this entire development. Okay, where this part is the perturbation that's applied, and this is the PPV, perturbation projection vector, right? So it's the orthogonal component to U1, which is the tangential vector of the limit cycle, right? Which is the velocity of the limit cycle. So it's the orthogonal complement to the tangential vector. Okay. All right. And of course, alpha of 0 is equal to 0, which is the initial condition you need to solve this differential equation. So given the PPV and the perturbation, and you know the initial condition, obviously alpha of 0 is equal to 0 because at time equal to 0, there is no perturbation, or there is no phase shift. Given the initial condition and this differential equation, you can solve for alpha of t and find the phase shift given a particular perturbation, right? So that's the, and also note that this is a non-linear differential equation, right? Because v of t is a vector and you have t plus alpha of t. So in general, this is a non-linear differential equation. So basically alpha of t is not linear with respect to perturbation in general. All right. So we have kind of derived what the PPV is, but there are still some parts that are left, which I think should be done. So we still haven't really shown that this B tilde term does not produce any phase shift, right? So we've shown that B1 produces only a phase shift, but we haven't shown that B tilde, which is the orthogonal, not exactly orthogonal, which is the other component in the perturbation, does not produce a phase shift. So we haven't really shown that. Okay, so let's actually do that now. So this is a theorem. It says that B tilde of x comma t produces only amplitude deviations that are bounded with time. So what does that mean? That means that no matter what B is, even if there's a continuous perturbation to the system, the amplitude does not go to infinity, whereas the phase actually does, right? So in other words, xs of t plus alpha of t plus some z vector of t, right? So that's the amplitude perturbation. This thing essentially solves x tilde, sorry, x dot equal to f of x plus b1 of x comma t plus b tilde of x comma t, which is the capital B times small b, the summation of these two. Let's actually write that out. Plus capital B of x times b of t. Okay. And the most important part is that it's bounded, right? So we said that it's bounded. So what does that mean? Another way to say that is that where z of t goes to 0 as time goes to 0, if the perturbation is removed after certain time. So after a certain time tc, if I remove the perturbation, then the z of t should go to 0 as time goes to infinity. Okay. So this is essentially the same thing as saying that amplitude perturbations die out in a limit cycle, but we're kind of making it more formal. Okay. So I'll give you like a quick proof of this, but it's not going to be very rigorous. But this is the general idea of proof, right? So I'll say maybe the idea of the proof. It is the full proof actually, but I'm not very careful with the calculations. So, okay, so we do the same thing. We basically take this term and we substitute it into this, right? So ddt xs of t plus alpha of t plus z of t is equal to f of xs t plus alpha of t plus z of t plus b1 of xs plus z. I mean, I'm not writing out the entire terms because it just becomes too long. B tilde of xs plus z. Okay, very nice. So now what I can do is I can expand this f in terms of Fourier Taylor series around xs for a deviation of z, assuming z is small. So if it's a small perturbation or a small change, then we can write f of xs plus z as f of xs plus the Jacobian df over dx transpose z, right? Plus some higher order terms, which I'm going to ignore. When z is small, I should say modulus of z is small. Okay. All right, so substituting that back in the equation above, we get implies that xs dot of 1 plus alpha dot. I'm not writing out the expanded terms, but this is essentially what you get, is equal to on the right hand side xs dot, which is exactly this term, It's the same as what we did earlier. So I'm kind of being a little bit quicker, right? And this can be written as A, which is what we did again at the beginning of the video. We did the Jacobian to be A of t. It's the same A of t actually. So we get the same state transition matrix even. Plus B1 plus B1 tilde. Okay. And we saw that in the previous case, this term cancels with this X and B1, right? So we just left with Z1 tilde is A of t Z plus B tilde of XS plus Z, which is now an inhomogeneous linear, I should say inhomogeneous linear differential equation, right? And we saw in the beginning of the video that such a solution to this equation can be written as Z equal to summation I equal to 1 to n exponential of mu I t ui vi transpose of 0 times Z of 0, which was the homogeneous solution, plus the particular integral, which is I equal to 1 to n ui of t integral 0 to t exponential of mu I t minus s vi transpose b tilde ds, right? And of course, z of 0 is 0, right? Because there is no perturbation in the beginning. That term goes to 0. And then we are left with this term where b tilde is again given by this summation here. Where is it? This summation here, right? Okay, so we are left with actually two summations now. B tilde is summation I equal to 2 to n ci mu I, right? So we have one summation here and another summation in here actually. And if you kind of look at this term, we have ci times ui, and here we have vi transpose, right? So when I equal to 2, for example, only v for this I, so maybe I should use different notation, different subscripts. So maybe we'll use j for this. Right? So you have a summation over I and j, and if j is equal to 2, then this summation only fires when I equal to 2, right? Because of the biorthogonality conditions here again. So essentially, if you go through and calculate the different, like you'll see that a bunch of terms basically drop out, and you're only left with this summation. You're only left with this summation, right? Because I equal to 1 term doesn't have that biorthogonality complement. Okay, so you will be left with nothing but summation I equal to 2 to n ui of t integral 0 to t exponential of mu I t minus s vi transpose of s b tilde of xs comma t ds. Okay, and of course, since I is greater than is 2 to n, this can be written as b of xs b of t, because the b1 component is 0, right? Because for the, I mean, basically this is equal to b1 plus b tilde, but the b1 term doesn't have an orthogonal component in v, so it just goes to 0. So you can write this as summation I equal to 2 to n ui transpose ui of t integral 0 to t exponential of mu I of t minus s vi transpose of s times the perturbation xs of s times b of s ds. Okay, so that's it. So essentially, what do we have here? We know that modulus of the exponential of mu I t is less than 1 for all I greater than or equal to 2, which is what we did in the beginning. One of the lemmas that we showed had this property, right? That all the flow k exponents are less than 1 for I greater than or equal to 2. So this means that z of t is always bounded, right? So all of this essentially becomes just a scalar factor, and which is bounded, constant, is within a constant factor of b of t, and hence it's bounded. Okay, so that's a proof, I guess. It's more like an outline of a proof. You have to be a little bit more careful with how I've used this t here. It should not be t, it should be t plus alpha of t in some cases, but the final result is the same. You get something like this. So, okay, so what have we shown so far? We've shown that any perturbation can be divided into two components, one along the tangential component of one along the limit cycle velocity, and one that is not exactly orthogonal to that. It's in some other direction, and that is determined by the C1 factor, right? And all of this we spoke about more as an overview in the beginning of the video. So now we know exactly how to calculate for a given perturbation and the PPV vector of a given oscillator or a given limit cycle. What is the phase deviation and what is the C1 value, which determines the projection onto that specific vector. And that's why it's called a perturbative projection vector. So let's do a specific case where we have impulse perturbations. Right, so similar to ISF. Let's see what this gives us. It's just to ground ourselves a little bit. So I say that this is of the form some b bar, which is just a vector times delta of t, right? Where this b bar is some impulse. Okay. So we know that b bar of delta of t, b bar times delta of t can be decomposed into two parts, which is the phase deviation part and the amplitude deviation part, as we did before. And that can be written as C1 times U1 of 0 delta of t. Because we saw that B1 is nothing but scaled version of U1, right? Where U1 comes from the flow k vectors plus b tilde of delta of t. And we have a differential equation for alpha of t, which is C1 of excess of t, comma alpha of t, comma t. And that's nothing but C1 times delta of t, which is this part, right? And of course, it's a very trivial differential equation. If the derivative of a function is a delta function, then the function itself is a step function, right? So which means that alpha of t is 0 if t is equal to 0, and it is equal to C1 if t is greater than 0, right? And this is similar to an ISF, if you remember. So this is saying that if I have an impulse excitation, and if you look at the component along the tangent, then if that component has some amplitude C1, U1, then the phase that is generated is a step function, right? So in that sense, it's similar to ISF. Okay. And also xs of t plus alpha of t is nothing but xs of t plus C1 now, because alpha of t is equal to C1 when t is greater than 0. And we know that that solves x dot equal to f of x plus b1 delta of t. which is nothing but f of x plus c1 u1 of 0 delta of t, which is f of x plus c1 xs dot, because u1 is the same as xs dot, delta of t. It's just writing out the different ways in which they're equal, I guess. Okay, and we also know that C1 is V1 transpose of 0 B bar, right? And that comes from the bi-orthogonality condition, which means that alpha of t, which is a phase shift, is V1 transpose of 0 times B. Very important again. So it's just the product of the PPV function, right? This is the PPV, and this is the impulse amplitude, right? And here it's a vector, of course. I mean, this is a vector and this is a scalar, right? This is a scalar. Okay. And we know that from the theorem, we know that the B tilde component does not produce any deviation as t goes to infinity, right? Because we said that it doesn't produce any phase deviation, and any amplitude deviation starts to die out once the excitation is removed. Since this is an impulse excitation, of course, the excitation is removed after no time almost. So essentially the impact of B tilde goes to 0, right? So which means that the asymptotic phase or the long-term phase is given by VI or V1 transpose of tau, actually, B tilde, B bar, if the impulse is delta of t minus tau. So if you have an impulse at tau, then the phase shift is given by the PPV vector times the impulse amplitude. Okay, so if you actually go to Cadence and try to simulate this, since we are working with two-dimensional systems, B bar, the impulse, is a one-dimensional quantity, and the PPV vector is also one-dimensional because we only look at it along the tangent. That makes sense. Okay, so they're essentially very similar to ISF. Okay, one last concept I wanted to talk about quickly is the concept of isochrones that show up in these kind of systems. We won't really do any derivations, really. We'll just look at what the concept is. So if I have a limit cycle, we said that, okay, this has two components at every point. If I move along this direction, probably I will get only phase shift along the tangent. It's not exactly the tangent, but along some direction. And then along some other direction, which need not be orthogonal, let's say this direction, then I don't have any phase shift, and I look at it asymptotically, right? Long-term behavior. There's no impact. But that is for a specific perturbation, right? So that is for the perturbation that is given by this vector, right? I've decomposed it into two components. But what if I have a different perturbation, right? So if I have, let's say, something that's long, something that's bigger, then what happens? Then I will have some other vector now, which gives me no phase shift. So basically, I have a large number of vectors that give me no phase shift, right? And they all pass through, of course, this point, because if I have no perturbation, then I have no phase shift. And then on the other side, maybe they look something like this. So I have a lot of these vectors that all give me no phase shift. And the locus of all of these vectors is maybe something like this. That's called the isochrone. Okay, so It's essentially the set of perturbations that do not contribute to the asymptotic or long-term phase of the oscillator. So every point actually has its own isochrone. So it could be something like this, right? Something like that. Of course, they don't cross. So this shouldn't be like that. This shouldn't be like that. Okay. So maybe something like this, right? So ideally, if you can design an oscillator where the perturbation to the oscillator from some charge being injected moves along the isochrones, then you will have no phase noise anywhere, right? So in that sense, they're very useful, but it's very hard to compute them. And I don't really think it's very easy to design oscillators based on this. But maybe it's possible. I don't know. So with that, I would like to conclude. It's already quite a long video. We've covered a lot of topics. Just to quickly recap, let's go back all the way up. So we started with PPV model. We said ISF model has this kind of makes this assumption of orthogonal decomposition. We said, okay, maybe that's not exactly correct. The right way to decompose is to say that I have a specific vector along the tangent of a certain size. And that is the right decomposition. And that gives you like an oblique basis decomposition. And then we recap some of the previous video on Floquet theorem and state transition matrices. And then we derived from that some basic preliminary equations, which we used a lot. We started with oscillator dynamics, and we showed that there is a limit cycle solution. If there is a limit cycle solution, then its velocity of that limit cycle also satisfies, actually the velocity satisfies a homogeneous differential equation. And since it's a homogeneous differential equation, which is periodic, it has a Floquet decomposition, and that Floquet decomposition gives us Floquet vectors and Floquet exponents, which we use quite a lot. We showed that one of the Floquet vectors, arbitrarily, we chose that to be the first one, is along the tangent to the limit cycle, and it has a Floquet exponent equal to 1, which means that the other Floquet exponents must be less than 1. And then we went into the nonlinear perturbation analysis. We said, given a perturbation to the system of a certain type, it can be decomposed into two parts, the B1 and B tilde. And B1 only produces a phase shift. And we showed that this B1 is intimately related to the PPV and C1. And basically the phase C1 and PPV are intimately related. And we derived some intuition based on that. And then we went on to say that this B1 pushes or pulls the state along the limit cycle. And we also calculated the value of C1 using the bi-orthogonality relations from the Floquet decomposition. And finally, we found the differential equation which governs the phase shift as a function of the perturbation and the PPV. And finally, we showed via a theorem that the other component, which produces only an amplitude deviation and no phase deviation, is bounded. First of all, we showed that it only produces an amplitude deviation and not a phase deviation. And we also showed that that amplitude deviation is bounded and goes to 0 when the perturbation is removed. And we did kind of a sketch of a proof, I guess. It is a proof, but we're not very careful. Okay. And then finally, we said, okay, taking in impulse perturbations, we get a result similar to the ISF, where an impulse produces a unit step function in the phase shift. And that is given by the PPV and the amount of impulse excitation. And we showed that, okay, the B tilde component need not be orthogonal to this B1, and its response dies out as time goes to infinity. Finally, and we ended with this notion of this concept of isochrones. Okay, so that completes, I think, the PPV theory, at least the derivation of the first half of, not first half, sorry, the first, I guess, the basic concept of PP, where it comes from. We haven't really looked at how this translates to phase noise, and I may or may not do that, but this should give you definitely enough background to go and look up that, but it's should be good enough. Okay, in the next video, we'll look at how to simulate the PPV. That should be much, much shorter, just 5 minutes maybe in cadence. Okay, thank you so much. Hopefully it was enjoyable. I know it's very long and maybe very technical, but should be useful. Okay, thank you. See you in the next one.